Welcome to the deep dive. Today we're going down a pretty fascinating and maybe even counterintuitive rabbit hole. We're looking at the architecture of large language models and specifically this research that's suggesting a causal link
Right.
between an LLM's ability to draw, simple diagrams, and its actual overall intelligence, its ability to reason.
It sounds almost like a party trick, doesn't it? Like asking if being a grandmaster at chess makes you a better baker. But the thing is, the correlation is it's really robust. Our sources are showing that the highest capability models, the ones we think of as having real reasoning skills, they don't just get better at language. They also get, well, incidentally, much, much better at generating valid scalable vector graphics, or SVG.
So the natural first thought is, just intelligence makes you good at everything. A rising tide lifts all boats.
Of course. You're smarter, so you can draw. It's a side effect.
A side effect. But the core mission for this deep dive is to explore this really audacious hypothesis they're calling reverse causal enhancement. Is this just a correlation, or can we actually use focused training on structured drawing, what they call SVG-First training, to actively induce better reasoning in a model?
Exactly. We're asking if the path to better logic might actually run through, of all things, geometry, and SVG is the key.
Okay, so for anyone listening, maybe just a quick refresher on what SVG even is.
Right, so it's not like a JPEG or a PNG, it's not pixels, it's a text-based format, it's code. It uses XML tags to describe geometric shapes, their coordinates, how they're transformed.
So geometry as code.
Precisely. And this whole proposal argues that by forcing a model to master the really extreme structural rules inside that code, we can fundamentally change its internal organization for the better.
We're not just teaching it to draw better. We're using the act of drawing to reorganize its mind.
That's it. It's like we're deliberately inserting a missing dimension into the current scaling laws, which have mostly been about just, throwing more and more text and code at the problem. This is about structural quality over just textual quantity.
Okay, so let's unpack that. Structural quality. I mean, text has structure. Code definitely has structure. Why is SVG so special? What's the signal in there that you can't get from, the entire internet?
It all comes down to the tolerance for error. Think about it in terms of local flexibility versus global constraint.
Okay.
Natural language is locally flexible. It's forgiving. If I say something with slightly sloppy grammar or use a metaphor that isn't perfect, you still get, 99% of my meaning?
It's robust against noise.
Absolutely. The model just has to be coherent from one word to the next. But with SVG, you're in a world of global constraints.
You mean?
Meaning a single token error, a misplaced coordinate, forgetting to close a single tag. It doesn't just make one part look weird. It can invalidate the entire diagram. The whole thing just fails to render.
Wow, that's a massive penalty. So the model can't just guess the next most likely word. It has to hold this entire coherent plan in its head across maybe thousands of tokens.
That's exactly why the sources argue this raises the cognitive bar so much. It forces the model to do several really hard things all at once.
Like what?
Well, first, maintaining long-range dependencies. If a line starts at point A and it has to connect perfectly to the center of a circle that's defined 500 tokens later, that relationship has to hold.
I see.
Then there's enforcing hierarchical structure, understanding that a diagram is made of nested groups, not just a flat list of shapes. And finally, preserving relational coherence, like knowing that if you rotate a group of shapes, the coordinates of every single shape inside that group have to change in a consistent way.
So if the model is being forced to mentally juggle all of these geometric rules before it even spits out a token, what's the supposed payoff inside its latent space?
The proposed benefit is that this stimulates the emergence of what the research calls structured object-centric latent subspaces.
Okay, that's a mouthful.
It is. Think of it like this. Instead of the model's internal mind being a big, messy jungle of word associations, it becomes more like a well-organized library. A library with a specific, pristine section just for geometry and spatial relationships.
So instead of trying to represent, say, a square with just a bunch of, fuzzy associative text vectors,
Right.
it actually starts to build a dedicated internal component for what an object is and how it relates to other objects.
You've got it. It's building a foundational internal geometry engine. And we know from other AI research that these kinds of object-centric representations dramatically improve a model's ability to do algorithmic and relational thinking. This SVG training is basically a curriculum designed to force that evolution.
It forces it to organize itself.
Yeah.
You mentioned a term in the sources, representational entropy. Can you simplify that?
Sure. Think of the model's internal space as a giant tangled ball of yarn. When it learns from text, the thread for square might be all tangled up with the thread for red or happy. High entropy just means it's a disorganized mess. SVG training forces the model to untangle that ball of yarn, to create clean, separate spools for concepts like position, size, and relationship. That clean organization, that low entropy, makes doing logic and math way, way easier.
That makes the causal argument much clearer. But
Yeah.
here's the hard part for me. We all accept that a smarter model can probably draw better. But we're proposing the reverse, that focused drawing practice makes the model smarter. Isn't there a huge risk that we're just overfitting it on structured data, that it won't generalize to the messy real world?
And that is the absolute critical challenge to this whole reverse causal enhancement hypothesis. It all hinges on the mechanism of how it changes the model. The argument is that these demands drive fundamental changes in how the model processes information, not just what information it processes.
Okay, so let's break down those drivers. What makes the error signal from a broken SVG so much more powerful than, say, from a text hallucination?
It's all about the precision requirement. I mean, if a model makes up a historical fact, the error signal it gets back is often fuzzy. It's grammatically fine, just not true.
Right.
But if the SVG model hallucinates a coordinate, the rendering engine breaks. The geometric rule is violated. You get this immediate, dense, and really high magnitude signal of failure.
It's a huge, unambiguous red flag saying, you are wrong, and this is exactly where you went wrong spatially.
Precisely. A much clearer target for correction. The second driver is hierarchical planning. To make a complex diagram, the model has to internally simulate the final product, the nested structure of a circuit, for example, before it even writes the first token. That mental simulation, that is a form of multi-step planning.
And the third driver, this latent-space regularization, that's where the internal geometry engine gets built, right?
Yes. The curriculum acts as this powerful regularizer, forcing the model to be consistent with geometry and composition. It learns abstract rules like parallel lines never meet, which are fundamentally logical, not just statistical patterns in text.
So if we build this robust internal geometry engine, the payoff, the transfer scaffold has to be real. How does mastering, coordinate transforms in a drawing actually help you solve a calculus problem?
It's all about analogical transfer. If a model has truly mastered manipulating coordinates within a complex transformation, it's essentially learned the generalized skill of performing structured operations on abstract things. That knowledge can transfer directly to, say, algebraic manipulation.
So understanding how rotating a square changes its coordinates, that skill transfers to understanding how to apply a function transformation in algebra.
Exactly. Or mastering the nested groups in SVG transfers directly to understanding nested logic in code like if statements inside for loops, which current LLMs can really struggle with. It provides the relational foundation that robust logic needs.
Okay, so to make this work, the research proposes a pretty systematic staged curriculum. You can't just throw a million random diagrams at the model and hope for the best.
No, absolutely not. It has to be progressive. It's designed to shape those internal representations in a modular, hierarchical way. The sources lay out 6 specific stages that really build on each other, almost like the developmental path for a child.
So walk us through that. How do you go from drawing a line to actual semantic reasoning?
It starts at the very beginning. Stage 1 is just primitive shape encoding. Can the model flawlessly represent a circle, a rectangle, a line? That's it.
The basics.
The absolute basics. Then, stage 2 adds transformations and alignment, teaching it to move things, scale them, position them relative to each other. This is where concepts like next to or twice the size of become spatially concrete.
And then we start building more complex logic.
Exactly. Stage 3 is compositional layouts. Now it's combining dozens of those primitives into complex grids or patterns. This demands planning across a much wider set of tokens. But the real workout starts at stage 4. Constraint satisfaction.
What's the challenge there?
This is where the model is forced to make sure geometric rules are met under pressure, making 2 complex shapes perfectly tangent, making sure everything aligns to a hidden grid. This is where even minor spatial errors are heavily penalized, forcing that clean internal organization.
So it's not just drawing a picture anymore, it's solving a high-precision spatial logic puzzle.
Yes. And that's what prepares it for stage 5, semantic diagrams. Now it applies that geometric skill to things that have meaning. flowcharts, electrical circuits, molecular bonds.
Ah, so it's not just a box and an arrow. It has to understand that the flow in the circuit diagram has to be consistent with the actual logic of the circuit.
Precisely. It integrates the structural thinking with domain knowledge. And finally, stage 6 is text-integrated SVG. This is where it learns to put labels and annotations on the geometric structures, explicitly connecting that clean internal world of geometry with the much messier world of natural language.
You know, the really clever part of this whole plan, from a practical standpoint, seems to be the data itself.
Oh, absolutely. This solves a massive bottleneck in AI training. SVG datasets can be generated synthetically by an algorithm.
Which means they're automatically, what, perfectly labeled?
Perfectly labeled, and you can programmatically verify if they're correct. Unlike human-labeled text, which is always noisy and subjective, you get access to a virtually unlimited supply of perfect high-signal data with very low human cost.
It's the perfect noise-free sandbox, designed specifically to teach deep structure. But let's play devil's advocate one more time. We're training it in this perfect synthetic world. How do we really know the skills transfer back to the messy, real-world problems? The proof has to be in the reasoning, right?
That's a crucial point. You have to measure the transfer, not just the SVG scores. And the proposed experimental design is really rigorous. They'd test an SVG-enhanced model against a control model that's only been trained on the usual massive diet of text and code.
What specific reasoning gaps are they hoping to see close?
They're looking for clear wins in high-level cognitive tasks. So things like better chain of thought consistency, better multi-step planning, and significant gains on tough math benchmarks like GSM-8K and the math dataset. And because of that transfer scaffold we talked about, they also expect to see big improvements in code reasoning on benchmarks like human evil, where that hierarchical logic is just so important.
And to really prove the hypothesis, they have to look inside the black box, don't they? Better performance isn't quite enough.
That's where the latent-space confirmation comes in. They have to validate the core claim. They'd use diagnostic tools to actually find those internal structures they predicted, the object-centric subspaces, the hierarchical modularity in the SVG-trained model, but not in the control.
So if you see the structures and you see the reasoning gains, the causal link is pretty strong.
Very strong. They also expect to see practical benefits, like lower hallucination rates on complex problems, just because that internal geometry engine is constantly acting as a sort of a sanity check.
So to synthesize all this, for years we've just been throwing ever larger mountains of text at these models, hoping that logic and geometry would sort of accidentally emerge. This research suggests a much smarter path.
It's a high-leverage intervention. The idea that instead of these vast, expensive scaling efforts, a relatively small, highly structured curriculum could give you these disproportionately huge gains. It's a focused attempt to induce the world model behavior we're all looking for, which could make AI development more efficient and, frankly, more interpretable.
This deep dive has really laid out how shifting AI training toward these structurally constrained tasks like SVG might unlock the deeper geometric and relational priors that are necessary for true intelligence. It's a real challenge to the text-first paradigm.
It is. The proposal really suggests that this kind of structured path might mirror how human cognition develops. By mastering spatial relationships first, the model builds a foundational framework for abstract thought, which then helps stabilize its use of language.
And that brings us to a final provocative thought for you to consider. If the sources are right, and SVG training induces structures that mirror human cognition, does that mean that for an AI to achieve robust reasoning, it needs to learn basic geometry and spatial relationships before it masters advanced language? Just like a human child develops object permanence before they become fluent. What does that imply for how we design AI curricula in the future if the order of learning turns out to be more important than just the raw volume of data?
It's a huge challenge to our text-first assumptions. It suggests intelligence might require a cognitive developmental roadmap, not just a massive data feed.
A fascinating point to ponder. Thanks for joining us for the deep dive. We hope this exploration into structural priors gives you plenty to think about.